Should Neil start? Neil wants to know if he should start. Sorry, what?
Is it a break or do I start now?
Break? Does he start?
Okay. I know that. I just. All right. So this is kind of an interesting situation. I mean, you know how Jason operates. He like doesn't tell you anything, and so I knew about this workshop, but I didn't really know what it was supposed to be. And then last week I thought, well, I'll ask him. You know, maybe he's that interested because they don't know about R, or that's not something you can hack on that easily, or whatever. And so I thought, well, I'll ask him how many people does he think will attend. And I was thinking maybe 3 or 5, in which case I don't have to do any work. But he said expect 100. I don't think so. I think the answer is actually somewhere in between. But my reaction was, holy shit! That means I actually have to go and do another set of slides just for this, which I wasn't anticipating. And then we've gone from that to an embarrassment of riches because I think, and this is kind of I think what Jason has in his mind also, is that what happens is sort of dynamic. So by way of example, last night, I mean, I had more interaction with people in that pub, and so many things came up, and all of which are sort of related to what you've been talking about with monitoring. But we went into this whole other space about how you do the analytics on that and what performance metrics meant and other examples and so on. So this went on endlessly and amongst all sorts of different people last night. I was lucky to get out of there with my life. And I was thinking, you know, maybe, in a sense, maybe that's the more important thing. You know, screw R, but I'm not going to do that. But I was just thinking, you know, maybe R sort of just receded in the background. It's just another thing. And now the question is, what should I really be talking about? And so, in a way, it's a little bit up to you. Any people here were discussing stuff with me last night? Oh, they're probably all taken off now. So nobody's answering that. So all else failing, what I'm going to do, how many people here are familiar with R at any level? So, okay, and so I'm not quite sure exactly where to begin. So I put together basically a quick tour, but this tour is not like the ones that you'll find on the web. I mean, it's quite easy to find guides about how to use R on the web and so forth. What I've done is I put together some notes based on kind of what I went through when I went up the learning curve. Such things as, where the hell is that file? You know, how do I get it? And what does ls do? ls doesn't do in R what it does in the Unix shell, right? It's the same command, it's kind of there. They're sufficiently similar, but they're different. And this drove me up the wall. So I started to write these things down just so I could, you know, learn it myself. And then I generally give this stuff out to people who attend my classes on this subject where I do the data analysis class and so forth. So I thought I'd just start off with that, and then we can launch into anything you like. Not that I'll necessarily be able to answer it, but I'll just sort of start off, and then I'll walk you through some of these things, and we can pick up on that topic. Or if you have other questions, I can try to answer them. The other thing was concerning me: if you were going to try to hack something, you know, what would that actually mean? Which actually I think is a very interesting question. I just think it's a rather deep question, and it's not clear to me how that would occur, particularly this late stage of the day. Anyway. So I'm just going to kind of ramble on a little bit, just show you, you know, just in case, obviously there are some people who haven't seen R before. So basically, I gave a little bit of the history the other day, yesterday when I did my keynote. So R goes back to Bell Labs also, just like Unix, and there's a certain amount of parallelism in the history. The legacy is that the interface to R, as a general statement, is very similar to Unix shell. I mean, a lot of the ideas are very derivative. And in fact, you know, one of the giveaways is that, yes, it's another one of those things that uses a single letter as a name, just to screw you up when you try to Google it. So here, and I generally use it on the Mac. So what you're seeing here is the Mac. I thought I'd try to split the screen here a little bit. I don't have any fancy tools for doing that, so I just thought I'd put, this is the R console. So how many people actually have R up and running here at the moment, have it installed and running? Okay, so you can follow along. It's worth it. So this is the console. In Windows it will look a bit different, in Linux it might look a little bit different, but basically the same functionality. And so this is the equivalent of your shell. but it understands R command. So I can, for example, just do 1 plus 1. It understands that means 2, which you can't do in the shell unless you do, expression or something like that. So it has a certain context that it's carrying with it, or it understands how to do that. And that's because it's an interpreter. And the other thing that you can do is that instead of doing it that way, you can actually bring up a little editor, and I could say 1 plus 1, and just keep that as a script. And then I'm going to put that into a variable name, just so I can, so I'll just call it var. I'm going to assign it the result of adding 1 plus 1. And the assignment operator in R is actually 2 characters. This is another piece of legacy. It was a single key. We had the same thing at Xerox, a single arrow key, but that kind of got lost along the way, so now it's 2 characters. You can also do an equal sign, but it's not recommended, but it will go ahead and act on an equal sign. You can also put semicolons at the end if you prefer that. These things are just tossed by the interpreter anyway, right? So I just take that, I'll save it. Oops, that'll be uppercase, foo.r, and I'm going to put that, I'll just put that in my little repository there for R scripts. So now what I've done is I've created a script. Instead of just typing things interactively into the console, which will eventually just go into the cosmos and be lost, I can put it into a script, and I can hack away in the console, and things that work out for me, I just cut and paste them back into the script and build the script up. That's how you do this stuff. As I mentioned yesterday, one of the key differences is that in Mathematica, for example, which I'm also very familiar with, there's no console. You're just basically writing a document with all the fonts, so you'd only be using this right-hand part here. This is the equivalent of Mathematica with all the fonts and everything. The interpreter's built in, and so you don't need to be cutting and pasting all the time like that. So then if I take that script, and if I can find it, so there it is, and I can just say open it, and he didn't like that. Let's see, what happened? Why is that a problem? I have to do print here, sorry. See if that helps. I can just reissue the command. There you go, sorry. So there's a slight difference. When you do things interactively in the console, you can just say 1 plus 1 and it'll return the result 2 and interprets that from the console. When I put it in the script, notice there's a slight difference. There's the same assignment. I've assigned it to a variable just so I can keep track of it. But then if you don't do anything else, it doesn't really know what to do with that at that point, because it's not evaluating it and putting it in the console, whereas it is here interactively. So I put in a print and the name of that variable, and then you saw it printed it out. Do you see what I'm saying? There's a slight difference. These are annoying little things that get in the way, but you get used to them after a while. So that's kind of that's the way it's set up. And then there are packages and so forth that you can bring in. I mentioned some of these yesterday. And the way I like to do this is, the typical Macintosh way. You have a package manager, which goes and reads all of the packages that you have currently in your local environment. And you see this sort of stuff here. And if you want to get something new, there's the installer. So you can give a package name here that you might be looking for, that you found out about on the web or some email or wherever, or Twitter. And you just put that name in there and get a list, and it goes out onto the major repository, which is called CRAN. This is the equivalent of CPAN for people doing Perl, or CTAN if you do LaTeX. This is CRAN for R. And you can just say get a list, and then we'll go and find out that repository that matches it, and it knows that you're using Mac OS versus Linux, for example, and just installs it, and you can say include any dependencies, and we'll just install that, and then it becomes part of your local environment that can be managed from here. You can do all of that also from the console as separate commands, but I like this GUI interface. It's quite nice to watch how that tracks. So that's just basically operational things. So let me sort of walk you through a couple of things. So the first thing you really need to understand is how to get help. So Mathematica, I'm going to make the comparison with Mathematica because that's what I use mostly. In fact, actually Mathematica is my native way of thinking about things, because there's things like plotting and so forth. I find so much easier to understand syntactically, just more intuitive to me. It's a pain in the neck. If you want to draw a sine curve, you can't just draw a sine curve in some range. You've actually got to provide the data points for it, and so on, because it doesn't have that paradigm naturally, because it's more directed towards looking at statistical data. Whereas Mathematica does have an idea how to plot a continuous curve in some range. It just understands what that means. So I generally find those sort of things much easier to do in Mathematica. And then in Mathematica you have inbuilt, the package includes the documentation, full-blown with examples, which you can also use and cut and paste into your document. R is not so well integrated. It does help. It does have help. But for example, if I say, I don't need to do help. Sorry, help. Let's see. Well, we were talking about mean before, right? Let's see that. So this is your typical help locally in the R system, and you can see, if you look at it kind of sideways, it kind of looks like a man page with a nicer fonts, right? But that's about it. But it does have some internal hyperlinks that take you to other things that may be related. And then the usual routine is it has this sort of man page type of usage and synopsis and all of that jazz at the top. If you're really keen to use something, you don't want to read through all this crap, you just go straight to the bottom and you'll find usually an example. And the nice thing is you can just take the example, because sometimes you just see the thing in operation, it's like, oh, okay, I get it. I don't need to read all that man page jazz. So here is the mean. So here we've got this variable x, which is being assigned a range between 0 and 10 with 50 points in it, and then it asks what is the mean, so it's going to use the mean function. Well, let's just try it. Who cares exactly what that means? Let's just throw it in there. You can throw the whole lot in, multiple lines together, hit the return key, and there are the values that it's computing. So I can look down in the main page and just select that as an example, feed that straight into the console and just see what it does. Sometimes that's the best way to go. You could do another thing like this. You can say, I hope this works, 1 to 100. Do you know that's a famous problem? I'm sorry, that's not quite right. Let me think. It's sorry. Sorry, that's it. You know that's a famous problem? What is it? Yeah?
Zero, right?
Gas.
Gas.
School child. Yeah, Carl Friedrich Gauss, a famous mathematician from the 19th century. When he was a school kid, the class was driving the teacher up the wall, so he gave them all a problem, which was to add up all the numbers between 1 and 100. And within minutes, Gauss gave the answer. And actually, you know what? I mean, he obviously had the insight, but it's really just, you just think of it like a histogram, a column of numbers. There's a triangle. It's half the base by the height. Try it. So anyway, so you can do these things just by using them operationally. That's what I do, because some of these packages are very sophisticated, and if you try to understand all of the underpinnings of it, you'll bury yourself for several days trying to understand the statistical mathematics behind it, all of which may be good and exact and correct. But the point is, I just want to use the damn thing because I've got other stuff I want to do. So you just cut and paste, chuck it into the console, you see how it works, you put in your parameters, and away you go into the next thing. And then you can go back and look at it later if you really have to understand it. But there's nothing wrong with that. I mean, that's fine. You can't understand everything. So, but anyway, that's the level of documentation. Now, the other alternative is to go onto the web. So, for example, I don't know if this all probably should work here, right? If I get rid of all this. If I go into Google, oh, give me a break. I was already logged in. So what I like to do is I would type R with some character in between just to try and help Google along. Often it does know what you're talking about, but sometimes it gets mixed up between a Python library or something like that. So I could just say that, and look what we've got here. R, so the R colon tells you this is the equivalent piece of R documentation, and if we look at that, look, isn't that what I was just looking at locally? So all of these local pages are also out on the web. Notice they're based in Switzerland for some reason. So it's actually ETH in Zurich. And, but then you can also, so see, there's other R things that are coming up here that are not necessarily to do with the R package, so you have to look a little bit carefully. Here's, if you didn't understand the mean, you can look this up here. This is a tutorial. There's quite a few of these websites out there which are a nicer form of documentation, much more readable. They take you through, it's not a man page, they're trying to take you through with some level of understanding, usually by example. And in fact, here we have a whole nice little page about how to define the arithmetic mean, which is actually the formula I showed you earlier. And then they give examples and so on. There's any number of these things out there now. So going on the web is your other alternative, and it's quite often the case when you're trying to do something a little bit squirrely, you go out on the web and you'll find, sure enough, somebody's done something, either the same thing or near enough that you can get it, you know. Another one is Stack Overflow. I forget, I can't keep track of all these different names, but there's a Stack Overflow has quite a few of the more highly technical questions and background on some of these functions. So basically, I would say generally I tend to use the web information because I've got many more alternatives come up quickly. I can pick and choose which things I want to look at. I also keep them bookmarked if I'm going to use them in the future, that if they look particularly good. And that's the way I tend to use it, rather than the local. I use the local stuff, but more rarely, I would say. So that's basically Help. Help 911 is a package I put together, which is actually, a lot of the content of this is contained in these slides, which we'll put up on the speaker site so you can get a copy of it. But I have this thing, let's see, let's see. No, so I have to load. So there's a function that I wrote, little package that I wrote. I think I have to call it. Called Help 911. So this is my little emergency help thing, which is what I'm going to be walking you through. And then once I load that as a library, now the R environment knows about it. It's now loaded in memory. In fact, if I do an ls, which we'll come to shortly, we'll see, where are we? HI. Oh, I thought it'd be loaded there. I guess it's not yet. All right, so then if I do now help.911 with parens on the end, the reason for the parens is because everything's basically a function. So it's like a shell command, but you have to put the parens on the end because it's actually a formal function in the R environment. So if I do that now, it brings up a PDF where I have listed here all the sort of things that have driven me up the wall while I was learning R. So, for example, get my data. Where is it? Well, you can read the data in through read table and so on, which I'll show you shortly. Other things are, for example, can I do an increment operator in R? This is something that is not obvious at all. The answer is yes, it's sort of there, but the actual syntax is a little bit squirrely because you have to put these % signs around this operator. So that operator, the plus operator, doesn't exist, but you can do the same thing with an increment in the way you would do it with C. After all, it comes from Bell Labs. But you have to put these % signs around. So because of the way the interpreter operates, you have to make allowances for that. So the answer is yes, you can sort of do it, but this is how you have to do it in R if you want to do it correctly. Can you do the trinary operator? Yes, you can. It's called if-else, which is actually nicer than the C syntax. But so this is just to give you an idea. So I have this online. I give this to my students when they come to the class, and I'm giving it to you here in this slide format. So another thing is I want to know what version am I running, because I might not necessarily have the latest version of the thing. So if I just type version in as a command to the console, notice I don't have to put the parens there. It's an embedded function, so it brings up the details about what machine I'm running on. And the reason I might want that is because I might put that into a script to remind myself I was running on that machine over there, not this one, when I did that analytics, and so forth. So these, by the way, you can't be too careful about doing this, because in a year's time when you go back and look at all this junk that you've created, what the hell was I thinking? And if you don't put this stuff in there, then you'll be asking that question for a long time. or you have to repeat it. So these things, as a performance analyst, these things to me are absolutely critical. So to be able to have a command like that version where I can just type the command, see what it is, cut and paste that into my script, for example, to keep track of these things is extremely useful. That's why it's on my list of 911 help. Another one is hardware. So this is very much machine dependent. So if you're doing it on the Mac, you can call this function system, which is the generic function, but the argument that you feed in quotes is specific to the environment. So it uses the system profiler in the Mac to get the information you see listed here. So this is what it looks like on the Mac, and your mileage will vary accordingly. Once again, tells me and documents for me, what environment was I working on when I did these calculations, and because there might be a gotcha in there somewhere down the line, and I can resolve it if I keep track of this stuff. So to me, this is just automatic, So to have these things available is extremely important. So what time is it? Well, it's just like the date function in Unix, right? So once again, parens on the end, I call that function date, and it brings up essentially the same as the system time that you're used to seeing. If you want to be more specific, there is this function called sys.time. I don't know if this will work exactly because I don't know about the actual characters. Yeah, that works. So this is the more canonical timestamp that you would see in monitored data. All right, this I know you've got down, this part, because that's your x-axis. Right, so UTC, whatever. I know you've got the x-axis right. It's the y-axis I'm a little bit more concerned about. So that's actually what you're doing. When you're showing all these time series and plots and so forth, you're using that canonical time form, but the date form is also available. It's a bit more human readable. Why do I care? Because this is what I do. When I'm putting a script together like I was doing here earlier, this is not actually how I'd start off. I would start off by saying, first of all, created by me on date, which is there. Just select that. That's the first line in every script I put together. Because then I know when I did it, who did it, and that means I can't blame anybody else, right? And then I start to put the stuff together, the code. And I also try to include as many comments as I can, because the intent behind the code is the thing that's always the mystery. So the more comments you put in, the better. Comments are easy, as you saw, is just a hash sign. So this would be, add two numbers. Oops. Add two numbers. We're done. That's cool. Save it. We're in business. So that's why I like to have that. This is all sort of the critical starting point before I get too excited and carried away doing some calculation. And then we get into things like converting time from human readable form into POSIX compliant time and so forth. This becomes more important when you're trying to plot in R, when you're trying to plot the x-axis. This is something that you already have, because that's how you're typically looking at your monitored data from all the examples I've seen over the last 2 days. In the case of R, it's a decoupled environment, so it doesn't know what you're trying to do. It can do whatever R is capable of doing. So the point is, I have to tell it that the x-axis is not just an index for the number of data points, but actually belongs to some particular time. What time? UTC, Pacific time. And so there are routines for handling all of that and breaking all that up, so that you get the correct kind of time values on the x-axis. This is something I think you don't have to worry about so much, because you're already doing that in your monitoring facilities, as far as I can tell. The only thing you would have to worry about is if you bring it into R, that they match up. So these, in fact, are two routines that I've written to do the conversion to POSIX time, or a number of hours or something, like lopping off all the minutes and seconds if I don't want it, just to keep the graph clean. So these are examples, and as I say, you'll get these slides so you can try these things for yourself later on. Then there's the whole business of converting from UTC or Greenwich time to local time zones. All of this is available also. So I can make this take a system time, which I showed you over here earlier, which is this one, and I can convert that to a different time zone by saying to take that time that I created here before and then reformat it as though it's a time zone belonging to, say, Melbourne in Australia. And then it will do the conversion for me. All of which is extremely useful and powerful. And then I can convert between time zones as I need to. Another problem, so I've created this stuff on the console so far, and this is now getting in my way. I want to get rid of all this stuff and just start afresh. I don't need to bring up a new console, I just clear the console. And it's a command. I can never remember the key sequence, so I do it always from the menu. But your environment will vary slightly, but I just do clear console and now it's to start over again. That doesn't mean everything's gone away, because if I do that ls to see, ls here means to look at what's in memory, not the file system. Those things are still in memory. It still knows about them. They're still in the interpretive environment. It's just I'm just clearing the console to get the flotsam and jetsam out of the way as I'm proceeding in using it. So there are different options depending on whether you're a PC, Mac, and so forth. Where's my file? So here's another one. So this is sufficiently close to the Unix commands that they just drive you nuts, because it's not exactly the same, but they're nearly the same. So if I want to know what directory I'm in, there's the commands. It's get the working directory with parens on the end. And of course it's looking always by default in the top level user directory. I can keep track of that, so I could say that's the current user directory, and then if I want to go to some other place, I say set WD, set the working directory to some other place, and then since I've kept the previous one in a variable, I can go back there whenever I need to, right? So I can switch around. So very much like Unix, it's just they're not direct shell commands, they're functions, and they're slightly different but similar. That's why I have the 911. Similarly, if you want to see what files in the directory, it's not ls, which is the Unix command for looking at the file system, it's dir. So it's more like, I guess, DOS in that sense. Probably because the ls was already used for the memory, looking at what's in memory, looking at memory objects. They had to choose something different, so they used dir. So ls shows you what R objects are currently active in memory. So R is in some sense object-oriented. There's various levels of the object orientation, which I won't go into. It's kind of a bit complicated, and it's sort of a little bit pseudo object-oriented. And this is kind of an evolving thing. So you can have quite different classes of objects in R, and this has evolved now such that, if I remember correctly, I think S4 is now considered to be like the class which has the most truly object-oriented attributes in it. But there's also S3 and so on. These things tend to be older and are not as object-oriented as you might think based on some other languages. So if I want to get data in, so suppose you sent me or point a repository to some data. The way I'm generally using it, I generally get it from a file, but clearly it could also come from a database. There are all sorts of variants of doing this. Here's the general setup. There's a read function. There's a read function. Read.table is the usual procedure for bringing in data from a file that's on your system. But I can also use HTTP calls and so forth. Also, comma set variables, the type of files produced by Excel and so forth are also. So R is pretty robust about these different kinds of file formats. And read table is the basic function. There are some other variants like read CSV. Also, it knows now whether the file's even zipped up. It will unzip it automatically, so you don't need to do separate procedures for all of that. So quite powerful in that sense. If you have a file that has a whole bunch of preamble stuff that you don't want to consider as data, then the way you would do that is to call the read table function the same way. You pass the name of the file into the read table as an argument, in quotes. It's a string. You tell it there is header information, and then you tell it to skip however many lines of stuff you don't want to consider. So basically your options are you're either reading stuff in as data, in which case you just skip everything that comes before the data, That's not necessarily the best option, because what happens is you get the data in, but you won't know what the column names are unless you remember what's exactly in the file. So what you generally like to do is you'd like to keep the line before the data begins, because that's usually the header information for each of the columns. So this would mean skip 23, assuming, say, for example, that 24 is the name of the column headers. Skip 23 will throw away everything preceding away, bring in the column headers, and that's what you'll see in the representation of the data in the console. So let's see if I can try to do this. I'm not sure the fonts will get in my way. So I just brought in something called local data, and that's how it looks. So this is another thing that's very useful sometimes. If you don't have a lot of data, I know you're usually talking about streaming data. If you don't have a lot of data, for example, I often have people send me files where they've got 2 columns. First column is the number of nodes or CPUs or whatever, or number of user processes, and then the second column is the throughput that results from running the workload on those number of CPUs or with that number of users. And it's, maybe 50 lines would be sort of typically a maximum file, because they only have 50 data points that have actually measured under these conditions. So rather than put that in a file, I prefer to do it this way. So I'm actually fooling read table into thinking there's a file, because I use this text prefixed before that. And in the quotes now, notice the quotes start here and end down here. In that string is now the 2 columns of data, but read table will read that in as though it was reading the ASCII characters in from a file. And then when it presents it in the console, when I say show me what local data has in it, it now shows me that it has 2 columns of data which it indexes separately. So this is 1 through 5, but column A represents something else, so it goes 2, 4, 6, 8, 10. That's the actual data, first data column. The second data column, column B, is whatever those values are. The reason for this indexing over here is because I can actually enumerate those rows and refer back to them as like indexing into an array. So basically, I've just brought in these 2 columns of data organized in this fashion, and the reason this is valuable is because I can take that and also put it into my script, right? So I could take this, should take it from there. If I take that and then just put that into my script, wherever that's gone. So there's my script that I started up before, and suppose I wanted to enter that in. That changes the fonts a little bit, but that's okay because it's bringing it up again. So now the point is that I've got the data that I'm going to analyze embedded in the script, so there's no chance I'm going to be separate the analysis from the data source in this case. Obviously, if you've got several hundred lines, this doesn't make sense. It's better to keep it in a file. Or if you're reading from a database or some streaming repository. But this is quite useful for some of the things that I do, so I like to keep the data as local as possible so there's no chance it gets decoupled from my analysis. Then you can take that same data and write it out. So the write function does the opposite of read, as you might imagine. You can just give that a file name, file.data. You can quote it or not quote it, and so forth. So any number of options to do that. So I know how to read data in from a file or some other source. I know how to write it out. And that's very useful also because I might want to keep that data separate from my actual script, so I can write it out to a separate file name. In Windows, these things vary. I think I'll just skip through that part. Now, if you have there's a function and you want to know what it is, the canonical way to do that is to put a question mark before the function name. So if we did, let's try that again. We just do question mark mean. It brings up that help. So if I didn't have the, I can also put it in there. Would have done the same thing because I have this sort of GUI representation on the Mac, so that achieves the same thing. But if you don't have that, or you prefer to always work from the console at command level, then doing a question mark before the function name tells you what it is. If you want to find out more about it, let's see what this does. This will tell you which package it's in. So a question mark tells you what the function does. A double question mark tells you where it is. which is also quite useful. Now, this brings me to another point. So I wrote this thing called help.911, that's my thing, which I'm showing you the results of. So if I do that, without the parens on the end, because if I want to call it, I've got to tell R, I mean this function, which means put the parens on the end. If I don't do that, what will happen is the interpreter sees that as a variable name, which it then looks up in memory, because it's an object, looks up that object and shows me what that object is. And in fact, in this particular case, I wrote it in R language. R is both the environment and the language name. And it's showing me the code that brings up that PDF when I issue that command. There are other functions, for example, if I do that with mean, it looks a little bit different, because what's happened here is the mean calculation is not done in R. It's being done in some other language, for example, C. And so you don't get the full representation because it's got this as a basis of binary object, which is now in memory, and it can't display that for you. So that's what you see. So, whereas here, it's just loading in the interpretive version of the R and shows me the actual R language. By the way, this is quite cute because I can see how other people implemented their functions if they're written in R. And you can learn stuff that way too. But the other point is more important, and this, I want to go back on this point that the previous speaker made about what's it called? The stuff that he showed us in the previous talk, the previous workshop? D3, thank you. The D3 stuff was, it's interesting, and particularly for geolocation data, and it's fairly new, right? So it has new capabilities which he was showing us. But remember, keep in mind one thing, that's showing you monitored data, just collected data and representing it in interesting ways, no question, but he's not doing any real analysis on it, okay? And I don't know what the actual capabilities of D3 are. I take it that they're mostly around that graphics and the 3D graphics and so forth, which is fine, but I don't think there's a lot in the way of analysis. There may be eventually, but I don't think there is right now. The point about it is that this is an interesting distinction between something like that that's currently being developed and R. One of the things that I find quite amazing about R is that I can't say it's not bug-free, but it's extremely reliable and extremely robust. And you have to ask yourself, how the hell did that come about? And part of it is just its age. It goes back to the mid-1970s, depending on where you want to start with the S language at Bell Labs and so on and so forth. But the modern incarnation we see today really came about the late 1980s. So let's call it 20-odd years or so. But what happened is, this is not obvious, and most people don't know this, the reason that it's so robust and reliable in terms of doing calculations is what I'm talking about now. When I run a function that it produces results, I can be very confident that what it's doing is correct, without having to go there into the code and analyze and make sure and check all the code myself, which would be, to take endless time. How can that possibly be? The reason is because a lot of the statistical routines that R uses have been developed completely independent of R. There was something called statlib around a long time ago, 20, 25 years ago, which had C code in it typically. There's also other codes written in MATLAB, for example, and so on and so forth. And there's interfaces to bring that stuff into R. And so what's happened is you've got to think that these people were statisticians putting this code together for their own purposes. They beat the shit out of it, made it all nice and smooth and workable, and then it's been deployed and been essentially, migrated its way into R through various paths. And that's why when you see the mean here, it's not showing you the code, because that's probably a piece of C code that got implemented God knows when. We all know it works, so it's just imported and you run it. That's it. And you can be very confident that it's doing the right thing, because if people are using it enough, they would have found any problems with it. And over a period of 20 or 30 years, things become pretty reliable when they're used so much. Right? Get the idea? So I'm saying this as a kind of a word of warning also, because, most of what you've been discussing the last 2 days is just simply data collection. What I'm talking about here is analysis, the beginning, how to do analysis just a few steps away from where you are. But when you're talking about analysis, it's a whole different ballgame. You have to have things that are completely correct. That's why I brought up about the harmonic mean. So you walk into this, minefield of things that can, blow up in your face when you least expect it, because we're not talking about data anymore. We're talking about massaging the data, trying to extract information. And these routines that are in R or whatever environment are really ways to transform the data into information. And you've got to trust that those transformers are doing the correct thing. Otherwise, you're all hosed up, your analysis is out the window, you just wasted your time. I'm very serious about that, because I can say that's absolutely true of R and Mathematica. Mathematica has been around also about 20 odd years now, started in 1988. And although it's a proprietary product, there's a lot of people that use it, and because you're paying for it, any problems get addressed pretty quickly, and depending on what kind of service level you have. For example, I get pretty much every correction that's made to Mathematica, which can come in every few weeks, patches and so forth, for things that are not new bugs, just things that have been found to be a problem in some new function they've created, and so on. So these things quickly get patched up. In the case of R, it's the open community idea, okay? But also that these things have been going on for so long. So either from time or just the sheer number of users, and statisticians use this stuff. So this is very serious stuff. So I can be very, very confident that what I do here is doing the right thing. Not to say there can't be bugs, and there's ways of handling all of that. But in general, I don't have to be thinking all the time, gee, I wonder if that's really calculating the right thing or not. That's not what I'm thinking. That's looked more like a shock horror, something went wrong. I have found a couple of bugs myself, unbelievable, and I had to actually resolve them in Mathematica to figure out what was going on. So actually quite a pain, but it's extremely rare. I've done that maybe twice in the time I've been using it. So I can have a very high degree of confidence. So the point is, the watchword is any new tools that take the data that you've been talking about monitoring and begin to analyse that data, the ball game changes. Things have to be looked at very seriously, and you have to have things that are absolutely trustworthy in order that the analysis that you're doing is correct. Plotting. So this is, of course, one of the big fortes of R. And here's a famous example. Now this actually goes back to John Tukey. So I'm just bringing in, this is a set of data that's already, so R comes with a set of known data which come from historical contexts. There's the famous IRIS data from Fisher. The one I'm showing you here happens to be a record of attributes to do with various kinds of automobiles that were produced over, 20 or 30 year period. And I've just brought that data in, so I've just said attach. Attach means put this into my local environment. The data file or the data object is called MT cars. I forget what the MT stands for. Now if I just plot that, these plot windows are actually normally a bit bigger when you're using it. This has been resized for the video display, but it's normally something like that, let's say. So I don't know if you're used to looking at charts like this, but this is actually, it's showing all the data, all the possible pairwise axes for all of the data that's in the data, and I can see what the data is because if I just type MT cars, that's the name of the data object, so I can see immediately what this stuff is. And now you see this is different makes of automobile, and it's showing miles per gallon, number of cylinders, the displacement, horsepower, and so on. Then these things have been recorded, and you can see also, where are we? Okay, this is not including the year. Some of them include the year that they were produced. But anyway, so this is just various attributes. This is the data object. It's also called a data frame in R. So I can see the data object I'm looking at, and what this is doing here is taking all of those column names and just plotting them pairwise. Now this might not mean anything in particular, but it shows you immediately where you see, look at this, you can see these sort of like striations in the data. that means there's something periodic going on there, because they're all falling along a line there, then there's another set falls along a line here, and so on. But if I was looking at these other views independently, this just looks like a scatter plot of points, right? But if I change the axis, which is the same as changing the orientation of the axes, I may see the data differently. In fact, what I'm seeing here then is it lines up in planes. So if my fingers where they intersect represents the cloud of points on the scatter plot, when I look on that particular dimension, I can't tell that this is actually periodic unless I can rotate the data into that dimension, and now I can see they stack up in planes, you see? So there must be some periodicity there. And the first question is, well, what the hell does that mean? But you see, this is the beginnings of the analysis. I'm not watching time series anymore. I'm finding out structure in the data, which is going to provide me with the information once I analyse what it is. And that's actually Tukey's motivation, John Tukey's motivation for doing the data exploration, with being able to rotate the data. You pick any three variables, because we're stuck in three space, you know, virtual on the two, and then take the mouse, essentially, this is even back in the early 1970s, and be able to rotate the data and look for this kind of structure, which has no meaning other than the visual process that gets all excited because it thinks it sees patterns. But that's okay, we're just doing exploration. It may turn out to be nothing, or it may turn out to be a side effect, but my attention has been drawn to it immediately because I can rotate the data like this, you see? That's Tukey's big insight. That's why Tukey trumps Tufty. So let's see, if I do that, where are we? So let me try something. I'm not sure why that's not working. MT cars on weight, comma, MT cars, MPG. Oh, so sorry. So if I just do plot. If I do plot MT cars, just plot the whole data, it looks like this. You see, this is now, I'm sorry, the thing I was showing you was actually a subset before. This is the entire 2x2 permutations of all the pairwise axes of all of those attributes that's in the MT cars data. So the way to read this, you see the label of the axes is down the diagonal. So this means if I want, everything in this row, the y-axis is MPG, miles per gallon. And so this plot, for example, is plotting MPG on the y-axis and number of cylinders on the x-axis. Do you see what I'm saying? If we go down here, we're looking at actually cylinder displacement. If we go down here, we're looking at horsepower. So notice MPG against horsepower is just some scattered data by the look of it. But if I plot the number of cylinders, look, it's lining up, isn't it? Of course, because they're integral values, right? But you see, there's a lot of stuff here. I wouldn't necessarily do it this way, but you can see even with that, almost my peripheral vision can pick up on that. And I'm just doing exploration, so it's like, oh, what's that? And the fact that it catches my attention, that's excellent. That's exactly what you want. You want to have tools that get that visual cortex working. Because we're not drawing any conclusions at this point. We're just hunting for stuff. We're hunting for structure. So this is one way to look at multi-dimensional data, pairwise axes, not three-dimensional, just pairwise. And so the nice feature here is that when I say plot MT cars, I'm actually telling R to plot all of this data, which is in these columns, right? What the hell does that mean? Well, it knows what I mean is take all of the data and plot it all in pairwise plots for me, all possible pairwise plots. So that's nice because, you know, I don't have to think of some magic incantation to get that effect. It just does that more automatically because it has some understanding of how to work with data from a statistical point of view. If you did plot like that in some other package, you know, we'd be trying to do a straight line or something like that, right? This understands, okay, I've got so much data here, what you really mean is let me see all these pairwise possibilities. Great, and there's the command, very simple. Now, then if I want to look at something in particular, what I did here, I can go back to it, I've already done it. There it is. This one says, I just want to look at the weight versus MPG. So that's, the weight is in that column there, in the middle, and MPG was the first column. So I just want to take those two columns of data and just plot those, obviously pairwise, X, Y. So the way you have to do that is you have to qualify a little bit and say, okay, with regard to the MTCAR's data frame, which is all of the data that you have, when you want to refer to one column out of that data frame, you put a $sign. Okay, not to be confused with Perl or shell scripting. And then the same thing, MTCAR's $MPG picks out those two particular columns, and when I plot them, it looks like this. So now that's a scatter plot. And what do you reckon? Any kind of a trend there, do you think? Maybe. I don't know. It could be. So it looks like it's plausible. So let's try and do that. Let's see how this works. I'm just going to... You know what? I think this used to work in a previous version. Now it doesn't work because I'm running into too many problems here. That's strange. Let me just do this part first. So what I'm going to do is I'm going to call a routine. Just write that a little bit differently. And the data is equal to MTCARs. So I'll just break this down a little bit. I think in the previous versions this worked before, and now something's happened in the latest release. It doesn't quite work that way, so I'll have to update it. So what I've done here is I've called this function LM, which means linear model, because that's what we're thinking is linear trend, right? That's what you told me. So I'm then saying, see if there's a linear trend for the Y values, which is the MPG, because that's what I'm plotting. So MPG, so actually, by the way, let me fix that up a second. I'll go back and do the plot again. Here's the plot routine. What I'm going to do is put labels in. So I can just say Y label, which is just Y lab, is equal, quotes, weight. Sorry, that's X. X label, sorry, is weight, and the Y label is MPG. Is that right? Sorry, got to be in quotes, MPG. Let's put it that way. I'll put it in that way. Why is it doing that? Yeah, I don't know, something weird going on with this video stuff, I think, but anyway. So what I've done is I put labels on the axis now so I know where I am. That's quite straightforward to do. Now I'm referring back to the data frame. I can give it whatever name I like. I've used the uppercase and so forth. So a weight against MPG. Now going back to this routine, I'm calling this function LM, which says produce for me a linear model where I take the stuff on the y-axis, which is MPG, and model that against the variable weight. And the data that I'm using, of course, is this data frame here called MTCARs. And in fact, it's gone and done it. So what it's done is, since it's a linear model, the linear model can only have two parameters. Do you know what they are? The slope, yeah, that's right. So I can and a line can be anything like this. Then what else can happen to it? The intercept, which means I can move it up and down this way also, right? That's the two parameters. So what's happened is the R function LM has just calculated for me what that is. It says that your intercept, as the position on the y-axis where it cuts the y-axis, is at 37.285, whatever, and your slope is minus 5.34, whatever. That's the slope. So It's calculated the intersection and the slope that goes with it, right? That's the two parameters. So that must fix the straight line. And what about that minus sign? What do you think about that? Right, because it's going from left to right downward. That's a negative slope, so that in gradient, whatever it is, should have a negative sign, right? And in fact, it does.
Back in the 70s, a car that weighed 0 pounds would have 37 miles per gallon.
Yeah. Now let's see. So what I'm going to do now is I'm just going to change that and do that LM call again, but I'm going to put it into a variable, which I'll just call cars.fit. So dot is just a naming convention, like an object, so cars, but, and this is just a variable name, you can call it anything you like. Then I'll call that linear modeling routine again. And now what's happened is it's put those values into that variable, and I can check that by calling coef of cars.fit. And there it is. There's those two values we just calculated before. And now I think if I do AB line of MT cars, does that work? Yes. So AB line, as you can imagine, A and B refer to the gradient and intercept, right? That's the two parameters. So draw for me a straight line which has, I get mixed up as to which way they're around, whether I think of A as the gradient and B as the intercept, but I think it's actually the other way around in the R language, but it doesn't matter. So take those two parameters, draw for me a straight line with the appropriate values of the intercept and gradient, slope, that you just calculated using the function LM. Boom. So you get the idea? So these are really quite powerful in that sense, right? I mean, once you learn to sling it, you can do a lot of things with just a few lines of code, because it's already carrying so much information about how to handle statistical data. And by the way, it's quite different from Mathematica. So in Mathematica, I'd have to do quite a lot of setup just to do the statistical stuff, because it's much more general purpose. Yes, sir?
Does it draw the line no matter what, even if those were random points and there was no statistical, or is that line significant or not?
Absolutely. Let me show you how significant. So I just picked out the coefficient values just so we could draw the line, but on top of that, it's giving me also all of this other statistical information which I didn't reveal before, which are in fact the error bars, which I talked about yesterday. Remember the Higgs boson with the little cluster bombs there with the little X and Y error bars? These are the error bars for those coefficients based on that model that's using that data from that data frame. So absolutely, this is the line of best fit, and it's using the linear least squares algorithm to calculate that, which is a standard statistical procedure. So all it's doing is really, it's just minimizing the vertical displacement between the line and all data points in succession. There's a formula for it, but what it's basically doing is says, okay, give me a line, trial and error, give me a line, and now calculate the vertical displacement from that line for every data point, add them up, well actually first of all square them so they're all positive, square them, add them up, and then try again, and if the next one you get is a smaller sum, that's a better fit. And it keeps doing that until it's optimized. But actually we already know the results, so we can actually write down an analytic expression which gives me the optimal best fit linear solution for any given set of data. It's just an algorithm, it's just obvious. Once you understand the statistics, we can just write down what the minimum must be every time. We don't have to use the trial and error, the variation principle, or anything like that. But that's kind of what it's doing. It's adjusting the line so that it minimizes the vertical displacement squared as a sum. That's why it's called linear least squares. The square just gives me a positive displacement because this is obviously positive up here. But what about this one here? Well, this is in the downward direction, so that would be negative. But if I square them, they're all positive then. And then I just minimize the sum of those squares, so that's how it works. So this is absolutely, this is not just any old random line. This is actually it's already a form of early correlation, you could say. Does that answer the question? Yeah.
So yesterday you had a graphic tool that had percent CPU usage, and then it was up hovering around 100%.
Yes.
Another line went up to 100%.
Yes.
After that, is that the type of analysis that you do now?
Sorry, I couldn't hear the last bit.
Is that the type of analysis that you could do now? Or how?
Yes, I did. In fact, that plot you saw yesterday was from R. However, it's actually way more interesting than what I showed you yesterday, and I was wondering if you would be interested to see the actual thing that I did. But I didn't do it in R originally. I did it in Excel. But who cares, right? What the hell? Tools for fools. The reason I would be quite happy to repeat it in R. The problem is, I was using weekly data, daily data over an 8-week period to do the super duper thing that I actually did. This was actually at eBay 1, so 10 years ago. They do things differently now. They know how to do capacity planning. But unfortunately, that data is missing. I don't know where the data is, so I can't reproduce the whole thing that I did at eBay in R because I don't have the data. But if you want to, I can show you how that works. Do you want to see that? I mean,
Yes.
I'm concerned that you get something that you can see the power of this stuff, whether it's R or I don't really care what tool you use. And it could have been done in R, except at the time I didn't know R. And by the way, all the managers and so forth, ultimately I had to make the case too. They all had PCs with Office on them. So, by the way, there's a very important point there. With regard to presenting data, it's not just necessarily about plots and all the visualization stuff I talked about yesterday. I mean, that's totally cool, and that's what we love to do. That's why we get up in the morning. But at the end of the day, those results have to be presented to somebody. In your case, it's the users looking at your monitored data. And you don't necessarily run into this issue, but it's something to think about. When I'm doing my stuff, I have to be very concerned, no matter what I do in terms of the analysis, when I present it to somebody that's the end client or a manager or something like that, I have to be very aware of presenting my results in their terms. And that and no more, unless they ask me. You know what I'm saying? Because if I don't communicate with them in the language that they're used to talking, it'll just go over their head and I will just waste everybody's time, including my own, because I won't get it. So the point is, I can't say, well, if you could spend the next few weeks understanding R, then I'll be able to tell you what my results are. That won't work. So I've got to go in their direction, which actually is usually easier, right? Because they can't take more than 3 bullet points. So you've got to pick the 3 bullet points and you've got to use their terminology. Example, when I was working at Pyramid Technology, I was sent to England to discuss resizing some big multiprocessor Unix boxes that we built for a company in England that produced, sold automobile insurance on the phone. This was before the web kicked in. And I quickly learned how to talk to them, because if you didn't talk about quotes per hour coming through the machine that's running an Informix database and all that stuff, they don't know about MIPS or CPU speed or anything like that. They could care less. They just want to know, if I buy this, how many quotes per hour can I push through that thing? The reason is because there's only 2 things in the insurance world: quotes and claims. Quotes are selling new policies. Claims are you have to pay money against an existing policy. They don't like that. Growing the business means you want to sell new quotes. So quotes per hour was their entire mindset. And if you didn't talk about the throughput of these Unix boxes in quotes per hour, they just wouldn't hear it. They wouldn't know what you're talking about. TPS, IOs per second, no interest, doesn't mean anything to them. It has to be quotes per hour. And then they listen. That's the difference, right? So it's like that. Well, I don't want to shortchange you on the R, but since this has come up now, this is the beginnings of what I did, where I showed you that plot where the purple curve or the blue curve is separating away above the CPU utilization data 100%. The technique uses this same idea, but instead of having just one variable that we're plotting against, it actually turns out to be 4. So it's called multivariate because it's 4 variables, not 1 variable, but 4. Multivariate. It's multivariate linear regression. So it's the same idea, except it's in 4 dimensions. But the routine's the same. Even Excel is quite happy with that. It could care less. But I'll just quickly show you that because I think it's really very interesting, and it's the payoff from doing this kind of analysis. And I think that, by the way, this is a reason I brought it up yesterday, because this is something that you could, for the people doing graphite and this kind of thing, add-ons to your existing monitored data, this is something that wouldn't take a lot of work, right? This is just a few steps away from what you're doing. It uses some fairly big machinery, but, you know, that's packaged and, you know, you don't have to understand that in great detail. So let me just show you that, because it is pretty interesting. So here we go. I'm not going to go through everything. I'll just show you that part that matters. So basically, you know, if you're just looking, this is the kind of thing I've been seeing for the last 2 days. What the hell does this mean? Noise rattling away. You know, something's happening, obviously, but what the hell is it? So, you know, no amount of endless staring at this kind of thing is going to get me anywhere, typically. And this cognitive processor, it can't handle it. It can't understand things this way. So I've got to do some kind of transformations in that data to get the information out. So that's what this is about. So this is a kind of a super duper version of what I just showed you, which was I used the routine called LM in R, which is linear model. In Excel, it's just called regression, I think, something like that. So let's skip over this. So here's the multivariate regression. So basically what we're looking at is this. So this is what you saw yesterday was just, these are data, right? So Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, Sunday. This is a week's worth of data. You saw just one of these yesterday. So you saw one daily. This is a week. And this is the data that's missing. I can't find the data, so I can't push it through R. This actually this looks like an unscheduled outage. So, you know, sometimes the time series tells you something. This is a negative peak. They're always not good. And then you see also each day is basically saturated. This is a 64-way E10000 machine running Oracle, saturating pretty much every day. And the dither point at the time was this back-end machine's $5 million a piece, fully loaded. And what eBay was splitting bullets over was, should they buy another one? And would it be worth it? And blah, blah, blah. And my job really was to show them that not only would it be worth it, you're actually behind the curve at the moment. So I had to show them this point. So this is what I did. So the way to look at this is that obviously in terms of data, monitored data, coming in this case from Solaris, I can't have data values above 100%. If I did, I would be extremely worried. Something's broken in the monitoring system, right? So this is completely correct as it stands. And this is, I think, you know, if you're doing monitoring stuff from an operating system, by the way, you're using the same damn counters that were put in there in 1970. Nobody ever stopped to say, wait a minute, is that really what I need to do performance analysis or capacity planning? You just stuck with it. That was put in there by kernel developers for their own purposes, not for doing capacity planning and performance analysis. Anyway, the point is that this is the data monitored from Solaris. This is collected and stored up in exactly the same way you've been talking about. But that's it. And I would say this is the kind of thing I've been looking at here for the last 2 days. And I can certainly see things like negative peaks are probably uncool. This is an unscheduled outage or something like that, probably. But then other than that, it's sort of just periodically oscillating every day. But there's some serious problems here. Obviously, they're out of gas, and they need some motivation to write that check. You know, that's really what it's all about. It's all about business. So what I did was, and I'm just skipping across all the details here. This took months to figure all this out. If I look at the incoming network data, which was on OC12 pipes back then, you can see that the traffic profile has this, what I call the numero uno signature, number 1. So it kind of ramps up, and then every night around 7 o'clock Pacific time, it would peak and then suddenly drop off. And a whole separate talk about what's going on there too, but we won't talk about that today. But you can see here, where you had no limitation on the data, because this metric is number of packets per second or something like that, bits per second, whatever. It's a throughput, it's a rate. Whereas this is CPU utilization, which is what of the 3 metrics? Which type is CPU utilization? Which one of the 3 metrics? Time, rate, or number?
number?
Very good. It's a number because the units on the top are time, busy time, and the units on the bottom are measurement period. Particularly the metronome, they're both time, so those time units cancel out. It has no units, so it's just a number. So this is just a number. This is a rate, and there's no limitation here. This is limited to 100% because the ratio, the D over T, the busy time over time, can't be bigger than 1 or 100% of the measurement window, right? So this is limited to 100%. This isn't because it's a different thing. It's a different metric. It's packet rate. And I can see the profile. Now you can see this is like, say here, this is like one of these with the fingers amputated. So suppose I could surgically reattach those fingers. What would it tell me? So I'll show you what I did. All right, so this is the raw data. Here's the model. So this is what we were just doing a minute ago with the LM function in R, was estimate the y-axis, which we call y-hat in statistics. And in that case, it's only one variable, which was also the weight or something like that. And then it told me, the LM calculated for me what the slope was, this is the alpha 1 here, and the intercept, which is beta here, right? Because we only had one variable. Here I've got 4. I won't go into too much what they are, because I stole the model. It's not even my model. Hey, reusable code. That's right. So this requires 4 metrics, which are coming from Solaris. Okay. In addition, and none of these metrics can be the utilization, obviously, because that would be too incestuous. I can't compute the utilization from the utilization metric. Doesn't make any sense, right? So these have to be something else. Turns out they actually come from the load average data, which I talked about yesterday a little bit. So there has to be 4 of them, so we won't go into that anymore. And then I did it in Excel. So here's the data. These are the 4 metrics, 1, 2, 3, 4. And some other numbers. There's the average CPU utilization as measured by Solaris. That's the data we'll be monitoring. And I'll do some jiggery-pokery, which I'll skip over. And then I'm left with some data that I'm going to do the equivalent of the LM on, but with those 4 variables, right? This is actually not a big deal. It looks like a big deal, it's not that big of a deal. And even Excel can do this. I'm using this data, which is the 4 metrics, the X1 through X4. And this is the thing I'm trying to estimate now. So this is the measured value, this is the monitored value, and I'm going to try now and estimate what that is based on these variable values, right? So I do the linear regression equivalent, and Excel tells me where the intercept is, so the same idea, and the slopes in each of the 4 dimensions, right? So no problem. Now then I go back into the spreadsheet, and I use the slopes and the intercept on each row, bang, 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 and calculate now a new value, which is the model value, we're talking about model, linear model, value of the utilization. And look, here we have something which is 120%, where the measured value, your monitored data, said 91.5. I mean, what does that mean?
It means you need 20% more capacity.
Exactly right.
The previous step was to test the model. That's how R squared is.
Oh, it was just running the model basically.
Hey, Dr. I'm sorry. I hate to cut you off.
Yeah.
I know what you're saying is much more interesting than what I have to do. But
If you look better.
It's bad enough cutting you off. It's really bad cutting you off looking like this.
It was your choice.
We had some lightning talks we want to do. So,
Oh.
And we're on the clock right now. So.
Well, I'm just looking at the slide there. Sure. So this is just running the model. I can look at the R squared value, and I see it's like 92%, so that's okay. But if I wasn't happy with it, I can play around with it a bit more. And then I go back and I start to plot that data, and that produces the purple curve. And then you can see that, can you see the index finger come back? But because I'm doing it statistically, it's a noisy finger. So I just created noisy fingers. I surgically reattached the fingers, but they're noisy fingers because I use statistics. And now you can see actually it's more like 150% during that week. So I just go to management and I say, what's happening is you're already using 50% of another E10,000, $5 million bucks that you haven't even begun to write the check for. And if you wait long enough, that number will rise to another 200%, and you will have completely wasted your money. That very night, they write the check. That's the power of analysis.
Awesome.
You get the basic idea? Yeah, good. I think that's pretty neat. So, well, he's telling me to get off the stage, so what can I do?